share with all of you this content. So I have the content. So the first is what is hydrological cycle and why one need to do the study this particular hydrological cycle. Then after studying this particular hydrological cycle, uh, yes, yes, sir.
इको क्यों आ रहा है? Because it is recorded. Quality इको आदित्य इको क्यों? Are you able to listen? इको आ रहा है ना?
Yes, sir.
इको आ रहा है ऐसा है, डबल साउंड आया।
इको आ रहा है सर?
हाँ, आपकी तरफ से और कुछ चालू है क्या? Is there any speaker?
Now, sir.
सर ते क्लासरूम हे असेल, खाली असेल त्याच्यामुळे येत असेल सर.
एक मिनिट सर है, मैं फैन बंद करता हूँ सर.
ओके
ओके. हाँ, जैसा रिबाउंड आ रहा है ना आवाज, तो आदित्य.
हाँ, थोडासा हे होते सर, ते क्लासरूम खाली वगैरे असेल त्याच्यामुळे येत.
रेकॉर्डिंग वर प्रॉब्लेम आहे का?
नाही नाही, रिकॉर्डिंग वर नाही सर.
ठीक आहे, कंटिन्यू प्लीज, कंटिन्यू. रिपीट व्हाट एवर. सॉरी, हाँ, सॉरी फॉर इंटरप्शन.
Hello sir, now my voice is clear sir?
Okay sir, okay, clear sir.
Okay sir. So these are my presentation content, the hydrological cycle. Then after having the certain impact, or you can say the knowledge of the hydrological cycle, then we go for the need of hydrological and hydraulic assessment and the simulation in a particular catchment or the watershed. So then with respect to a certain catchment, we have a certain challenges. So what are the various challenges in case of the ongoing catchment? So at this particular slide, I am going to clear with all these things. Then we have a different types of the models, okay. Then how do we can do the particular modeling in a particular catchment. Then the another is applications of various softwares or the models for the catchment modeling. We have different types of the software or the models we can use for the simulation and the assessment purpose in case of the growing catchment, such as HAEC HMS, SWMM, ECRAS, SWAT, MIC21. So these are the content I am going to deliver in the incoming slides. So basically, the hydrology is a Greek word, which means that the hydro means which is related to the water, and the logi means the study of various hydrological parameters in a particular watershed. So with the combines word, that is the hydrology means the science of water, so which deals with the occurrence, circulation, and the distributions of the water above the earth surface or the below the earth surface. Then we called it as a hydrology, okay. So it concerned with the water in a particular stream or lake, or the rainfall or the snowfall on the land, and the water occurring below the earth surface. So this is the certain fundamentals we have to understand in case of the hydrology. Then if you see this particular hydrological cycle, now in this particular hydrological cycle, if you see here, we have a certain the ponds, lakes, or the streams, or the even sea. So what is happening from there, this particular body, the water may get evaporate due to the sun rays, the water may get evaporated due to the heat which is generated by the sun rays. Then this liquid state will change its state in the another form, that is we called it as a vapor, okay. So the vaporization will take place in the form of the evaporations, and the evaporation will goes to the clouds. So there will be a formation of clouds. So at the formation of clouds, that stage we called it as a condensation. Okay. So condensation is the process where the cloud will form, and after the condensations, then there will be a precipitations. Okay. So the precipitations in the form of rainfall or the snow or the ice. Okay. So such kind of the rainfall or the snow or the ice will form over the ground surface. Okay. So some water may percolate inside the ground surface through the soil strata, and it become as a shallow groundwater, and after some years it become as a groundwater. Okay. Then after complete saturation of the soil surface, then some of the water may flows over the ground surface, and we called it as a surface runoff. Okay. And that surface runoff will meet to the particular stream or river, nala, and that particularly stream, river, nala will meet with the dams, then some ponds, reservoirs, and then ultimately this will meet with the sea. Okay. So in this particular hydrological cycle, we have to remember that there will be again certain evapotranspirations from the water body. Okay. Then evapotranspiration is from it is greenery. So we have a trees, we have a grass on the land surface. So depending upon the size and the greenery or the particular catchment. Okay. So depending upon that, certain kinds of the evapotranspiration from the water, these particular green trees will be there. So again, in case of the, if you see here, as the urbanization is increases, the imperviousness cover is also increases. So if you see here, in case of the urbanizations, okay. So due to the increase in the impervious surfaces, the runoff will be more, because there will not be any chance to percolate the water inside the ground due to the various types of the buildings, then roads, and then the impervious covers. That's why here the groundwater table is very deep, because there is no chance to percolate the water inside the particular area. But here, if you observe that the water table is near to the particular surface as compared to the urbanization. So such kind of the hydrological cycle or such kind of the fundamental we have to understand basically for any kinds of the catchment or the watershed. So here we have a different main components of the hydrological cycle. So the first component is the transportation component, that is the flow component. So in the case of the flow component, we have a precipitation. Then the second one is the evaporation, then the transpiration from the trees, then there will be infiltration through the soil strata, and then the surface runoff or the water body or the base flow also. Then another component of the hydrological cycle, that is the storage component. So as far as concerned with the storage component, the storage on the land surface, then we have a soil moisture, okay, then we have a groundwater. So these are the main component of the hydrological cycle. Then if you see the water distributions on the earth surface, so exactly if you see in this particular diagram, you can observe here 97% of the water which is available in the ocean, and only the 3% water is available as a fresh water. Okay. So out of this fresh water, if you see the 79% water is available in the form of ice cap and glaciers, okay, and 20% water is available out of the 3% as a groundwater, okay, and out of this 3% only we have a 1% accessible surface fresh water. Accessible surface fresh water means what? We have to use this particular 1% water for the purpose of the domestic water supply, then industrial water supply, and for the irrigation purpose also. So out of this 1%, the 52% water which is available in the lake, and then we have a soil moisture, that is 38%, and out of this 1%, the water within the living organism, that is which is present on the leaf of the trees, that is 1%. And again, out of this 1%, 8% water is available in case of the river, and then water vapors, that is 8%. So after having the knowledge of the water distribution on the earth surface, you may conclude that, or we conclude that it is very the crucial or the seriousness with respect to the water distribution system, because only 1% water is available in the form of as a accessible water for domestic as well as the industrial purpose. Okay. Then the major aspect with respect to the hydrology, Nilawar sir, my voice is clear now?
Yes sir, you are audible sir.
Okay sir. So here the major aspect of the hydrology. So we have the three aspects with respect to the hydrology, that is we have to collect the data, then we have to analyze the data, and we have to predict. So with respect to the data collections, we have different types of the data we have to collect, that is the rainfall, then temperature, then evaporation, evapotranspirations, then snowfall, runoff, groundwater, etc. Then what we have to do in case of the analysis, we have to check the consistency and the heterogeneity with respect to the analysis. So for example, we have a watershed, and in that particular watershed, there is the rainfall gauge stations. For example, we have a Siemens rain gauge stations, and it is not in working condition. So to establish the missing record of the rainfall at that particular stations, so we have the missing record, how to establish its relationship with respect to that station. So in case of the analysis, we can do this, and finding out the various statistical parameters. So this is with respect to the analysis of the data. Then after having the analysis, we have to predict. In case of the predicting the future scenario of different hydrological events such as rainfall, then its a peak value, that is the total runoff depth, peak runoff depth, and the lake time for the runoff in case of the any urban catchment or any watershed. Okay. Then we have to predict the flood and droughts events. Then we have to predict the how much stream flow will be there. Then the basin yield. So these are the predictions we have to do. So these are the three major aspects with respect to the hydrology. Then if you see the history and the importance of the hydrology, so history is very you can say the long years back with respect to the hydrology, but in today's scenario, almost all the you can say the technique which is coming in the modern days to predict all these things. So the hydrology finds its greatest application in the design and the operations of the various water resources project, such as the irrigation. Then we have a water supply, then we have to do the flood control, then water power, and then navigations. So almost all these projects, it required the very keen investigation with respect to the hydrological parameter, and we have to do the proper assessment with respect to the following factors. Okay. So the first one is we have to calculate the capacity of the storage structures such as the reservoir, then the magnitude of flood flows. Okay. Then the minimum and the quantity of the water which is flowing available at various seasons, and then the interactions of the flood waves and the hydraulic structures such as the levees, reservoir, and the bridges. So this is the importance behind the knowledge of the hydrology. Then the real problem will come across with respect to the any watershed. So the problem with respect to the any watershed or any catchment, that is we have to do the hydrological and hydraulic assessment and the simulations of the catchment. So these are the 5 parameters. If you study this parameter, then and then only I think so you can be able to do the correct hydrological and hydraulic assessment. So the first parameter, it is very important to study with respect to any catchment, that is the storm water. So the storm water is that water which originate after every precipitations. Okay. and which overflows over the surface, okay, of the earth surface in particular catchment. So we have to do the outlet for that particular storm water. So we have to minimize the flooding situation in particular catchment. So the storm water is an important aspect in case of the hydrological and hydraulic assessment. Then with respect to the urbanizations, so if the urbanization will take place, the imperviousness is also increases, and due to which the surface runoff and the lake time will affect, okay. Then the another parameter we have to take into consideration with respect to the any catchment or the watershed, that is the climate change impact, okay. So what do you mean by the climate change? Climate change means it is a long term, you can say, the change in the temperature and the precipitation for a longer period of times. For example, if you analyze 2020 to 2040, then 2041 to 2060, and then 21st century. So a long-term change in the climate factors such as the temperature and the precipitations, then this is also another important factor we have to consider in case of the catchment. Then there will be a changes in the future temperature and precipitations, okay. So with respect to a certain models, okay, that is the SDSM models, GCM and RCM models, we have to predict the future temperature and the precipitations with respect to the any watershed and the catchment. And then it is very equally important to study the non-stationary rainfall intensities in a particular catchment. So stationary means the magnitude and the time period for a particular rainfall event is the same throughout the catchment, but in case of the non-stationary rainfall, there will be a changes the magnitude and the time in a particular catchment, okay. Somewhere the magnitude is more, somewhere the precipitation time is more and the magnitude is less. So such kind of the variability we have to consider with respect to the non-stationary rainfall intensities. This is also important parameter with respect to the catchment, because the design of analysis and the design, hydrologic analysis and design of any infrastructure in a particular catchment depends upon the non-stationary rainfall intensities. If you do your analysis and the design with respect to the non-stationary rainfall intensities in a particular catchment, then you will be in a safer side, I can say. So this is about the 5 parameters we have to consider. Then these are the certain challenges with respect to a watershed or the catchment. So what are those challenges in case of the watershed or the catchment? So the first one is the correct assessment and the simulation of hydrological changes with respect to the magnitude and the, you can say, the time variance, okay. Then the another thing is that the challenges, that is the increase of stormwater peak runoff and its volume, okay. Then the higher mean and extreme flow, then the shorter time to peak and the lower base flow you will observe somewhere. Then excess runoff under climate change cause flooding. So the climate change is also a very important parameter we have to consider, because it may cause the flooding situations. So in the today's scenario also, if you see there, in case of the summer season also, there will be the precipitations in the form of rainfall, and due to which somewhere there will be a flooding situation. So it gives an alarm for us to take into consideration this climate change impact also in a particular catchment. Then extreme rainfall runoff and the hydrological parameter of a catchment for long period of time. Then the another challenges I would like to say at this stage, that is the change in frequency and the intensity of the extreme event in the particular catchment. So these are the major challenges in a watershed, but out of these particular challenges, we have another challenges. So we require another, you can say, the basic study. Then here the rainfall, you can say, is the one of the important parameter which operate the hydrology. So here the runoff depends upon the land surface. So the quantity of the runoff will depends upon the land use, land cover, then its vegetation, then what type of the soil will be there, because the runoff again will depends upon the type of soil, because some soil is having good holding capacity of the water, some soil is having the less infiltration capacity, more infiltration capacity. So depending upon that, the runoff will depends in any catchment. Then we have another parameter, that is the elevation, topography, and the slope. Then we have a drainage network, that is the surface ponds, which is available inside your catchment. Again, this is one other, you can say, for example, if you calculating the runoff, so you have to take into account that is any surface pond already will be there. So you have to do the study with respect to the surface ponds. Then again, the runoff depends upon the various the meteorological parameters, such as the precipitation type, that is the rain, snow, sleet, hail, then intensity, then their duration and their spatial distribution, prior amount, then the air temperature, wind velocity, and the relative humidity. So I would like to say that the rainfall depends upon, rainfall will operate the hydrology. Okay. So for this particular catchment or watershed, a fully integrated model we required to calculate the rainfall runoff process, then infiltrations, then evapotranspirations, then a stream flow by the various softwares, or you can say the models. So basically, what is a model and how it will work? So model is nothing but it is a program, or you can say it is a process. So it will require a certain input in the form of precipitation. So we have a input precipitation, or the you can say the temperature or the humidity or the infiltrations. Okay, so we require the input, then we have a processing. So in case of the processing, we have the computer program. In this, we have to do the process with respect to the various characteristics of the watershed. Okay, and we will get at the end of the by running this particular model, we will get the output in the form of runoff, or the particular you can say the stream flow. So this is what we called about or the process with respect to the model. Then here again, in case of the watershed, we have a watershed here, then we have a inputs. Okay, so hydrological modeling involves the applications of the mathematical expression that define quantitative relationship between the input, that is the flow forming factors, and the output, that is the flow characteristics. So we have required precipitation, temperature, wind speed, then solar radiations, then relative. Apart from this, we require land use, land cover, then soil type, then topography of the watershed. Then we will get, after the processing, we will get the rainfall runoff, the relationship, then evapotranspirations, and the base flow or the stream flow. So this is about the hydrological modeling. Then why modeling is required? That is the another question in front of us. So modeling has become as an integral part of the decision making process for various water managers, various stakeholders. Okay, for water resources engineers. So in recent research in hydrological modeling tries to have a more global approach to the understanding of the behavior of the hydrological system, to make better predictions and to face the major challenges in the water resources management. Then recently we have the hydrological model have taken over the most important task in the problem solving in hydrology, UNESCO 1985. It is valuable for studying potential impact of the change in land use or land cover. Then there will be a change in the climate. Then, as one report of CSDMS, that is the Community Surface Dynamic Modeling System, at present we have 56 hydrological model. Okay, so we have the 56 hydrological model. We have to do the study with respect to any watershed, and then we have the different types of the modeling systems. So we have a hydrological modeling, that is the black box. Then we have the conceptual, then deterministic. So with respect to the deterministic model, we have a lump semi-distributed and distributed model. So another forms of the model, that is the empirical model. So empirical model based upon the simplified experimentally derived relationships such as the linear regressions, okay, and physical model derived from the equations describing the conservation of mass, momentum, and any other energy equations. So we have the model that is VIC. VIC means the infiltration capacity model, okay, that is the VIC model is the form of the physical model. Now another model, we have the event and the continuous model. So event based means we have a storm, okay, so one storm 9 a.m. and it, so such particular model we have a HMS or the SWAT model. So continuous means we can do the simulations to calculate the various hydrological parameters. Continuous model means for monthly, yearly, we have to compute all these things. So there are many other types of model. So the further details, if you want to gain with respect to certain event and continuous model, so I would like to suggest that this is a good paper. You have to go through this particular good paper, and you will find that there will be more about the event and the continuous based model. Then the lumped model. So with respect to the lumped model, if you see here, we have a catchment. In this particular catchment, this is a stream which is flowing in this particular directions. So lumped means what? The entire catchment is considered as a one unit, and in this also the various watershed or the catchment characteristics such as the vegetation, soil, and other characteristics we can taken as a unity. So there is no any division or no any other sub basins with respect to the lumped model. Okay. Then the another thing is that the semi-distributed model. So we have a semi-distributed model here. So this particular semi-distributed model means what? This is a particular catchment, and then we have a stream or the river which is flowing through the particular catchment. So what we have to do with respect to the semi-distributed model, we have to divide this entire catchment into the sub basins. So according to our objective to find out the rainfall runoff or any stream flow. So depending upon that objective, we have to divide entire catchment into the sub catchment. So these are the examples of the semi-distributed model, that is the SWAT or the HMS. Then we have to know about the distributed model. Okay, so distributed model means what? The entire catchment is divided into the grid or the cell. Okay, so it is a complex model, but as compared to the lumped and semi-distributed model, this model will give the more accuracy in the output. Okay, so if we have to divide entire catchment into a particular grid, okay, or the cells, so such kind of the model we called it as a distributed model. So we have a MIC she or MIC 21 or VIC is the. If you compare the accuracy with the lumped and the semi-distributed model, the accuracy of this particular model is very high as compared to these two models. Then if you see, you can say this is the lump. Okay, entire catchment is considered as a one unit. Then in case of the semi-distributed model, we have to divide entire catchment into the sub basins, sub watershed, and then in case of the fully distributed model, we have to assign each grid cells. Okay, so this is about the parameter comparison with respect to the lump, semi-distributed, and the fully distributed model. Then the next things we have to understand the criteria for selections of the hydrological model. So we have a criteria. For example, we have a space discretization. Okay, then we have the another criteria for the selections of the hydrological model, that is the hydrological process, then vegetation layers and the soil layers. Okay, so in case of this space discretizations, we have a lump, semi-distributed, then distributed. Then in case of the hydrological process, if you do the criteria for the selections, then we have the empirical approach, then conceptual approaches, then physical approaches. Then with respect to the vegetation layers, we have the evaluation measure to select the model that is a single layer or two layer or multi layers. Okay. Then with respect to the soil layers, then we have the conceptual representations, then explicit soil depth, then finite difference or infinite element discretization. So I would like to suggest you have to go to the weather 2002. So with respect to that, a simple model structure does not reflect the complexity of the rainfall runoff responses, and a complex model structure is not always supported by the available data. So a balance between the complexity of the model and the available information is crucial for the successful model identifications. Then we have the another things.
Sir, sorry for the interruption.
Yes, sir.
One of participant is telling that please go slowly. They are making notes. So can you go a little bit slower, please?
Okay, sir. Okay. So which slide I would like to repeat?
No, sir. You can continue, but
okay, sir. Okay. So here we have the model for the selections. Okay. So we have different types of the model. Okay. Hague HMS. Then we have a SWAT model. Then MAICTE model and the VIC. Okay. So the Hague HMS is a hydrological modeling system. Is designed to simulate the rainfall runoff process of the drainage basin or the watershed. Then the main advantages of the Hague HMS is that it focuses on the runoff, channel routing, and the water control structures. Okay. So, for example, we have a different weirs or the you can say the notches. So this Hague HMS again controls such structures. Then the main disadvantages with respect to the Hague HMS is that the suitable only for events, not for the long-term hydrological simulation. So it is, if you see the limitations or you can see the disadvantages, that is, it is suitable only for the event, not for the long-term hydrological simulations. Then we require the empirical equations to calculate the runoff. So we have a SCSCN methods, that is the soil conservation service car number methods, to compute the runoff with respect to the Hague HMS. Then a base flow or the ground flow, then again we require the empirical equations to calculate the base flow or the groundwater flow. Then the another parameter we have to consider with respect to the Hague HMS, that is the small to large. Then the climate regime, that is rain or the snow. Then snow or glacial melt. So it account the snow or the glacial melt again. Yes. So for example, if you do the analysis, for rainfall runoff calculation in a particular catchment which is in the high snowfall region or the high glacial region, then this Hague HMS can operate in that particular region also. So after the analysis part, you will get the output, that is the full hydrograph, that is the FH. Then AY, that is the annual yield. Then PF means we have the peak flow. Then LF means the low flow. Then SW means the snow water equivalent. Then the ET means the evapotranspirations. Then we have a WB, that is the water balance. Then okay. Then ET, that is the evapotranspirations. Then IF, that is the infiltrations. Then we have the WB, okay. Then we have the WT also, the water table. Then we have the SM. SM means what? That is the you can say stream flow, okay. So these are the parameter we have to get in the form of the output with respect to the Hague HMS. So here we have the abbreviations. OF means the overland flow, then SF means the shallow flow, subsurface flow. Then we have the groundwater flow, that is GF, this abbreviation. which is used with respect to the output for all these models. So the another kind of the model, that is the SWOT model, that is the soil water assessment tool, soil and water assessment tool, which primarily focus on the water quantity and the quality and representations of the groundwater flow. Also, we can calculate the stream flow as well as the sediment with respect to any catchment. Then the main disadvantages with respect to the SWOT is the snow process representation require the improvement. Then these are the equation we require to calculate the runoff, that is the empirical again. Then it is a physical process. Then watershed scale, small to the large. Then rain or snow, okay, climate regime. Then also it is applicable for the snow, glacier melt regions, and these are the output. Then AICTE also. So AICTE is an integrated hydrological modeling system for simulating surface water flow and the groundwater flow. So AICTE can simulate the entire land phase of the hydrological cycle and allows the component to be used independently, or you can say the customized to the local needs. Okay, so it simulates the component complete land phase of the hydrological cycle. So if you see the disadvantages, but this is a commercial software. These two are the commercial software, and this basic two model, that is the AICTE HMS and the SWOT, is the open source. Okay, but these are the commercial software. So the main disadvantages with respect to the MIC, that is the simplified representation of our cost cover, then high purchase cost. Okay, then again we require the physical, you can say the parameter to calculate the runoff. Then it also required the physical process. Then it is applicable to the small to large. Then yes, it is for the snow. So all these are the software, you can say, having the more advantages as compared to the disadvantages. But at this stage, I would like to say from these observations which I have, as per your objective, as per your the watershed scale, and as per the simplicity of the output, okay, you have to select the model. Then we require certain inputs to run the model. So these are the geospatial inputs. Okay, so we require topographical, okay, then meteorological, astronomic, you can say the input to run the model, then land surface. So we require the DAM. Okay, so these are the source where the DAM you can download. So SRTM or ASTER. Then DAM derivatives, that is we have to calculate the slope. Then all these things is already available with respect to the DAM, that is the digital elevation model. Okay, the flow directions, then flow accumulation, then drainage network, then watershed or the sub-basin boundary or the area, then longest flow path or centroid or the flow from the centroid, etc. Then we have the another parameter we have to give as an input with respect to any model. So meteorological or astronomic, then the rainfall. So you have to collect the rainfall from the generally IMD department, Indian Meteorological Department. Then we have the data, we have to collect the temperature data from the NCEP, NCER, okay, or from the IMD department also, National Center for the Atmospheric Research, that is NCAR. Then radiations we required, AIRS. Then relative humidity, you can also collect this data from this particular site. Okay, then we require the land surface, then the land use, land cover, we got from these things, Landsat, spot, then soil moisture, then we require the land surface temperatures, then albedo, then evapotranspirations, then snow cover area, and the snow water equivalent. So these are the geospatial input we require to run a particular model. Then again, we require the another, you can see the data set for the, you can say the running of the model, that is the topo sheet. So this is the source where you can obtain Survey of India, SOI, then thematic map, that is the National Bureau of Soil Survey and the Land Use Planning, that is the Nagpur, India. Then we require the satellite data. This data you can be obtained from National Remote Sensing Agencies, that is NRSA Hyderabad. Then we require the daily, hourly and the rainfall data in the form of the graded type. So you can collect the rainfall data as per your catchment, and that is the Indian Meteorological Department, Pune. So this is the period, dry period, then recharge period and wet period. You have to collect the data. So these are the data we required, and these are the source. Then the another thing is I would like to tell you with respect to the catchment modeling. So we required a certain softwares or the hydrological model for the catchment modeling. So I have categorized the software into 5 category, that is the surface water models, groundwater models, then water quality models, and the climate change models. And we have another other software. Okay. So as far as concerned with the surface water models, we have HEC-HMS, then HEC-RAS, then SWMM, MAICTE, MAICTE-21. Then for groundwater modeling and the analysis, we require the ModFlow, then SWAT model, then GMS, then GS flow model. Then we do the water quality model with respect to this model, that is Aquatos, then HSPF, then WASP, then EFDC. Then we have a climate change model, that is GCM, RCM, and SDSM, and the other software by which we can do the simulations, that is EPANET, water gems, then severe gems, river cat models. So I'm going into details. That is a small brief introduction with respect to the HEC-HMS. So HEC-HMS is a hydrological modeling system, and it is designed to simulate you can see the rainfall runoff process of a drainage basins or the watershed. So it is applicable, that is the HEC-HMS is applicable to river basin water supply and the flood hydrology. Then it is also applicable for small urban or the natural watershed runoff calculations or the flow forecasting. Or if you know the future urbanization impact, so this is also a good, you can see the model or the software. Then it is also applicable for the reservoirs spillway design. Then it is also applicable for flood damage reductions and the flood plain regulations and the system operations. So this is the beauty of this, you can see the HEC-HMS. Then we have a HEC-RAS, that is the Hydrologic Engineering Center and River Analysis System. So Hydrologic Engineering Center for River Analysis Systems is a complex program that model the hydraulics of water flow through the natural river and the other channels. So with respect to the HEC-RAS, we can calculate the free water surface profile, then we can calculate the critical depth, the critical velocity, then specific energy with respect to the river or with respect to the channel. Okay. Then the another software, that is the SWMM, that is the storm water management model. Okay, SWMM. So storm water management model is used throughout the world for planning, analysis, and the design related to the stormwater runoff, combined and sanitary, you can see the sewers and other drainage systems. So with respect to the SWMM, you can plan, you can analyze, and you can design with respect to the any drainage systems. Then we have another software, that is the MAICTE software. So with respect to this MAICTE software, it is an the integrated hydrological modeling system for simulating surface water flow and the groundwater flow. Okay, that is the beauty. You can model the groundwater as well as the surface water. Then MAICTE can simulate the entire land phase of the hydrological cycle and allows the component to be used independently and customized to the local needs. Okay. So this is a commercial software. So it requires a huge cost for the purchase. Then the another you can see the software for the groundwater model. Okay. So for the purpose of groundwater model, we have the ModFlow. So ModFlow is the US Geological Survey modular finite difference. You can say finite difference flow model, which is a computer code that solve the groundwater flow equations. That is, it simulate the flow of groundwater through the aquifer. That is the beauty of that ModFlow software. So you can simulate the flow of groundwater through the aquifer. Then we have another, you can see the software or the model, that is the SWAT. Okay. So my voice is coming, Nilawar sir?
Yes, sir. Yes, sir. You are audible.
Okay, sir. So the another software, that is the SWAT, that is the soil and water assessment tools. So it is a small watershed, okay, to the river basin. That is the applications of the SWAT model used to simulate the quantity and the quality of surface and the groundwater and predict the environmental impact of the land use, then land management practices, and simulate the climate change as well. Then SWAT is widely used in the assessing the soil erosion also. Then soil erosion predictions or the preventions and the control. Then we can also calculate the stream flow with respect to the SWAT model, and we can do the sediment analysis in a particular stream flow. So that is the applications of the SWAT model. Then we have another model, that is the GMS, that is the groundwater modeling system. So GMS means the groundwater modeling system. It is a 3D, you can say you can obtain the 3D layers, one-dimensional, two-dimensional, or three-dimensional with respect to the groundwater flow. So I would like to highlight this model in incoming slides. Then GSF-LOW, that is GF flow model. That is, it is a couple groundwater and surface water flow model. And the beauty of this particular GS flow model is that we can do the couple groundwater and surface water flow model with respect to the rainfall runoff processes. Then you can say this is the applications of this particular model. Then we have the another model, that is the water quality model, that is AICTE-QIP-FDP-on. That is, it is a simulation model for aquatic system. Okay, this model is particularly used for the simulation of model for the aquatic system. It predicts the fats of the various pollutants such as the nutrients and other organic chemicals and their effect on the ecosystems. Then the another model, that is the AICTE-QIP model, that is AICTE-QIP model simulate for the for extended period of time. Okay, extended period of time, the hydrologic and associated water quality processes on a pervious and impervious land surfaces and in the particular streams. So AICTE-QIP uses the continuous rainfall, okay, and the other the meteorologic records to compute the stream flow and the hydrograph and the pollutographs. So you can do with respect to this particular model or the software, that is the stream flow simulations and the pollutographs or the hydrographs. That is the beauty of this particular models. Then we have another model, that is EFDC. Okay. So, or before that we have a WASP. So WASP, this model helps for the user for interpret and predict water quality, okay, responses to the natural and man-made phenomena, okay, and EFDC model, that is environmental fluid dynamic code, that is the long form of this EFDC. Then it is a state-of-the-art the hydrodynamic model used to simulate the quantity system in one-dimensional, two-dimensional, or the three-dimensional system. So this is the water quality model. Then we have the climate change model, that is the GCM, global climatic model. Then we have the RCM, that is the local climatic model, and we have to simulate in the SDSM, that is statistical downscaling model. Then we have the other, you can say, the software, that is the EPANET, WaterGens, SewerGens, and river flow model to design the drainage systems as well as the flow forecasting in the rivers. Then here I am going to discuss the another, you can say, first model, that is the groundwater modeling system, that is GMS, that is the groundwater modeling system. So if you see here, the GMS is the most advanced software, or you can see the model which is available for the groundwater flow simulations in the 3 dimensions. So we have a watershed. Okay, now if you simulate the flow below the groundwater in 3 dimensions, so we have to use the groundwater modeling system. So in 3-dimensional environment. Okay, so this is the beauty for this particular model, that is it interacts with the model in 3 dimensions, then create a photo in the realistic renderings. Okay, we can do the renderings also. Then we can do the animations or for the PowerPoint or the web presentation by creating the 3D. Then the annotations means we can do the add north arrows, scale bars, the reference images, or the company logo, and many more. So this is the applications of the groundwater modeling system. So we require certain input data, that is this model will require the input data, that is the raster image including the georeference and the projection supports. Then topographical maps and the elevation data. Then we require the borehole data including the stratigraphy and the geophysical data. Then we have to navigate these files in the modflow file. Okay, then we require the web data services such as the Terra servers. Then we require the ArcGIS data base and shape files to run this particular model. Then CAD files including .dwg, .dgn, and .dxf formats. Then worldwide projection support including the Cartesian and geographic systems. So we have to file import wizard for delimited text file and spreadsheets. Okay, so this is the advanced subscriptions or the subsurface characterizations for the this particular model. Okay, so in this diagram you can see here we can generate the 3D data to visualize the layers of the soil below the earth surface. Then we also calculate the cut cross section anywhere throughout the 3D data. Then 2D and 3D geostatics. Then we can create a solid from the horizon. So this is a applications of this particular softwares. Then I'm going to see the, you can say, having a case study on the HECRAS. So what is mean by the HECRAS, how it is applicable, and how we can run this particular model. So what do we mean by the HECRAS? So HECRAS is a hydrological engineering center for the river analysis systems. So it is a one-dimensional 1D okay model and design. It is required by the various hydraulic engineer for the channel flow analysis and the floodplain determination. So in case of the channel flow analysis, we have to find out the water surface profile for a particular depth. Okay, so for example, we have a channel. Then if you want to analyze the various hydraulic parameters, where is the critical velocity, then critical depth, then minimum specific energy or the specific energy. So we can analyze this, and also we can do the the analysis in the form of the graphical representation and in the table forms. Okay. So the HECRAS program was developed by the US Army Corps of Engineers to manage the river, harbors and other public works under their jurisdiction. Then the Hydrological Engineering Center in Davis, California developed for the river analysis, okay, to add hydraulic engineer in the channel flow analysis and floodplain determinations. So it includes the numerous data entry capabilities, hydraulic analysis, component data storage, and the management capability and the graphing and the reporting. So what we have to do with respect to the channel. So we have to create the such kind of the you can say select the stations. Then we have to create the geometry for a particular river or the stream or the channel, and then we have to calculate various hydraulic parameters. Then the uses of the HECRAS. So HECRAS is a computer program for modeling water flowing through the system of the open channel and the computing water surface profile. Then HECRAS find a particular commercial applications in the flood plain management and flood insurance study to evaluate the floodway enforcement. Then some of the additional uses are, for example, if you want to design the bridge piers, okay, or the culverts, okay, then in that case also we require the hydraulic data, okay. What should be the dimension for the bridge piers? So the dimensions of the bridge piers will depends upon the hydraulics of the rivers, okay. So once we have that hydraulic data, then we can design the bridge piers very easily. So these are the applications or the uses of HECRAS software. So then these are the advantages and the limitations, okay. So it's supported by the US Army Corps of Engineers, also acceptance by the many government agencies and the private firms. Now it is an the open source software you can download from the Google, okay, and you can simulate the hydraulic parameter in case of the river or any channels. Then it is available to download free of charge from the Hydrological Engineering Center website. So various private companies are also registered as a official, that is the vendor, and offer consulting supports and other ads on the softwares. So we have a certain limitations for this particular software, that is a steep bed slope. That is, if the slope is greater than 10%, then there will be a certain limitations. Then multi-dimensional flow characteristics, 2-dimensional or 3-dimensional, then there will be a certain limitations to do the simulation for 2-dimensional or 3-dimensional. Then complex pipe system, for example, we have a pipe systems, so it is complex. For example, in case of the industrial pipeline system, so it is very complex there. Then large data accuracy will require. So these are the some of the limitations. Then after having the good knowledge, if you have a good knowledge with respect to the HECRAS, what are the opportunity you will be get? So these are the opportunity I can say. You can do the floodplain and the floodway mapping. Then you can do the sediment transport modeling. Then we have the river and the channel flow modeling. Then we can do the direct rainfall, surface water and the local water course modeling. Then we can do the floodway identifications and the structure interactions. So these are the opportunity if we have a good knowledge with respect to the HECRAS. So the next thing is that how HECRAS works. Okay. So HECRAS contains 4 hydraulic components that model steady water flow, unsteady water flow, you can say the surface profile, then movable boundary, sediment transport, and water quality. So on the basis of this 4 hydraulic component, the HECRAS works. So the HECRAS model steady flow using the energy equations and the standard step methods, and for the unsteady flow using the Saint-Venant equations. So these are the equations we require to simulate the any, you can say, the stream or the rivers in case of the HECRAS. Then we require certain input. So we have a input in the form of the aerial map. Then we require DEM, that is the digital elevation model. Then we require the channel cross sections. Okay. So what we have to do, for example, we have a river or the channel for 5 kilometer or 2 kilometer, any length if you consider. So what we have to do, we have to channelize this for different intervals. Okay, so we have to do the cross sections. Then we require the land uses, land cover maps. Then we require the hydraulic structures. Then we require the sediment data. Okay, then the water quality, this data again we required to run the model. Then stream flow data. Okay, then water surface elevation and the discharge through the particular stream. So these are the input. Then in case of the processing with respect to the HECRAS, we have the steady flow water surface profile calculations. Then you can able to manage the free water surface with respect to the critical depth or the normal depth also. Then unsteady flow simulations you can do. Then movable boundary sediment transportation computation. Then water quality. So after this you will be get the output in the form of the hydrograph discharge. Then you can having the output with respect to the various cross section, with respect to the chainage distance you can calculate the velocity. So velocity critical also you can calculate. Then water surface elevations, then cross sections and the profile, then flood animations also. Then the flood inundation maps. So flood inundation maps means how much area will covered by the flood when the maximum rainfall occur in a particular watershed. Then we can have the output in the form of various graphs. So you can judge the discharge velocity with respect to certain chainage, and then we have a tables. Okay, so this is the you can say the input and the output with respect to certain processes with respect to the HECRAS. So this is a you can see the cross sections of the river analysis. This is a longitudinal section. So we have a flow in this particular channel. Then we have a free surface profile, and if you want to model the parameters with respect to the graphical user interface, so to run the model and visualize the result. Okay, so here we require certain input, channel geometry. Okay, then we require the chainages. We have to do the chainages. Then we have the left bank and right bank chainages, and we got the maximum flow depth, the critical depth also, and the water surface profile. So this is the, you can say, the input we require to run the, you can say, the HECRAS model. Then we will get the output in the form of the tables. Okay, so if you see here, we have the chainages. Okay, left bank and right bank we have a channel. Then on other sides we do the chainages. Then we will get the stream flow. Then we also get the area, then weighted perimeter for this particular channel or the you can say the river. Then percentage flow we will get. Then we will get the hydraulic mean depth, then critical depth. Then we will get the normal velocity or the critical velocity also. So these are the output we will get from the HECRAS. So I am going to show you the how we will get the output from the HECRAS. So Nilavar sir, can I share the one model?
Yes sir, yes sir.
Yes. So here you can see I have downloaded this particular HECRAS. Okay, this is a HECRAS model. Now here we have the various, you can see the command. Okay, various options. So here, if you see here, after downloading, many of the, you can say, the participant have the knowledge of these various commands, or you can say the here whatever make the option we have. So we have to edit the entire geometry data. So with respect to this command, then if you see here, edit or the enter the steady flow data from this option. Then we have another you can say the command. Then If you do the unsteady flow data, so you have to input that unsteady flow data to run the or to simulate the entire result. Then we can edit from the data from here itself. Then we have to give the sediment boundary conditions from this particular. Then here the another important thing is that if you want to import the open RAS mappers, so we can operate this particular open RAS mapper from this you can say the command, and then we have a view cross section. So if you want to after the complete input file, okay, which I have shown in the particular input, so if you have that, you can view the cross section of the particular channel geometry. Then we can view the profile also, that is we have a free water surface for a critical depth, critical velocity, and then we have a view general profile plot, and then we will get the rating curve also. Then visualize the 3D multiple cross sections plot also. Then we will get the hydrographs. Then we will have a you can say the detailed output for the culvert, bridge, or the weirs, and then we will get the view summary in the form of output in the form of tables. So I have already given the input, so I am going to just click the view cross sections here. So if you see here, after having the geometry, so before that I would like to click the geometry also. So here we have the geometry, okay. So for example, we have a 2 to 3 kilometer or 1 kilometer the area, okay. That is the length of the channel, okay. So we have to divide entire channel into the number of cross sections. So these are the cross sections, okay. So I have simulated here for my study area, that is I have selected the study area, that is the Bidkin, and under my watershed one stream is running or the flowing. So what I have done there, I have divided the entire stream into equal you can say the cross sections, and throughout the length of the channel. Then here, after having the channel cross sections, okay, so here we have the different options, okay. So we have to give the input, for example, okay, you have to give the input for the bridge or culverts, then for the 2D flow area simulations, okay. So this is after having the channel geometry and having the elevations also on left and right side of the geometry. For example, here 5.032 elevation, 5.081 elevations on left and right bank. Then what we have to do, we have to see the view profile, okay. Okay, we have a here profile, okay. So after giving the input to the particular stream or the channel, so see here how the water level will increase or decrease with respect to the elevation in a particular river. So if I click here, you can see here, so we have a the flowing of the water, that is we have a free surface flow, okay, with respect to the this particular station, okay, particular geometry or the cross sections. Then we have a certain elevations. So such kind of the fluctuation you will be get in the water surface profile. So we can understand, so what is the total depth, what is the total depth from the bed of the, you can say the channel or the river, and where is the maximum specific, you can say the minimum specific energy or the specific energy, then where is the critical velocity, critical depth. So with the help of this animation you can understand the beauty of this particular software. Then you can visualize the fluctuations in the water table, you can say the free water surface. So for example, I have created here, I am having the weirs, okay, in front of across the channel. Across means at an angle 90 degree to the flow, okay, in the channel. So if I simulate the water profile, so you can see here how the water surface elevation will changes. That is the free water surface profile changes with respect to the bed of the channel. Okay, for these particular weirs. Okay, so weir is a structure generally constructed across the flow in case of the channel for measuring the discharge. Okay, in a particular channel. So what is the flow condition on the upstream side and the downstream side? You can visualize with respect to the HECRAS also. For example, here we have the weirs, okay, and we have constructed across the flow in the channel. And if you want to observe the total depth, okay, height of the depth on the upstream side of this particular abstractions in the form of weirs on the downstream side, you can observe, okay. So this is a beauty of this particular software, and with the help of this, we can analyze what should be the total depth we required, or what is the total height we have to keep for this particular notch or weir, okay, and also how much length we require. So almost all the design of the weir will depends upon the hydraulics, that is the how much depth will generated on the upstream side and the downstream side, okay. So this is the another things I would like to show you. Then we have a you can see here the velocity, okay. So we can plot the various velocity, okay, with respect to the various you can say the times, okay. So for example, I have a velocity with respect to the 3rd Feb or 10 Feb 1999. So I can click that data and I can observe the velocity with respect to the channel, okay. So this is the velocity across the channel, and the velocity with respect to the right bank and left bank also. So these are the hydraulic parameter we will get. So again, if you click for the 11 February, okay, for the 12th, you can see the time, okay. As the time will changes, the flow in the stream is also changes and the velocity is also changes. So such kind of the velocity distribution diagram or the profile we can generate. The another things I would like to show you here, that is the another thing is that, see here what I have done here. This is a, you can see the channel, okay, or the river. So how much area will be flooded, you can observe by the simulation. So if I do the simulation, so I can observe the, you can see here, this is the area which is submerged. This area we call it as a submerged area. That is, up to this the water will flow in the river or the channel, okay. So you can do such simulations with respect to the HECRAS, okay. So such kind of the flood mapping, if you want to create, so you can create by this particular HECRAS. So you can having an idea how much water or how much area will submerge. So we can do the you can say the bank protections also. We can protect the bank of the river from the soil erosions also once we have the flood area map. So this is another applications of this particular software. Then if you see here, we will get the output, that is we have a chain edges or the you can say the time, okay, and we have the discharge in a particular stream or the channel, okay. So here we have a peak point, that is QP, that is the peak discharge, okay. So such kind of the graph you can obtain in case of the HECRAS. So this is another applications. And then if you see here, you will get the output. So if I see here, we have the output again. So we have a elevation, then velocity, then critical water surface profile, then energy line, slope, then total discharge, then top width, then velocity, maximum depth. So such kind of the parameter, with respect to that, we will get the values, that is the magnitude on in case of the channel. So here we have the so for example, top width 834. All these are in feet, so you have to convert into meter. Okay. So average velocity, then hydraulic depth. You can change the unit also. So such kind of the output we will get in the form of the, you can say, the tables. Okay. So another, if you see here, this is the total, you can say, the output we will get after having the, so we have a total discharge. Okay. Then main changes in the river or stream, then we have the water surface elevations, then critical water surface, then we have the energy lines or the energy elevations, then energy slope, then velocity, then we have the flow area, then top width, and also we can calculate the Froude's number. Okay. So if you see the formula for the Froude's number, V upon under root GD, so we can remark as a subcritical, critical, or the supercritical flow in the channel also. So what is the subcritical? If the Froude's number is less than 1, then we called it as a critical flow. And subcritical means if the Froude's number is equal to 1, then we call it as a critical flow. And supercritical means if the Froude's number is greater than 1, then we call it as a supercritical flow. So this is also very important things you will be get in case of the output with respect to the Hecras. So here I have another model, that is the SWAT model. Okay. Another model, that is the SWAT model, but as per the time restrictions, I cannot, you can say, the complete this particular SWAT model. So Nilavar sir,
Yes, sir.
Can I stop here?
Yes, sir.
Okay,
As you wish. Okay. Okay. If participants have any question, they can ask. Participant. Sir, I have one question. Can we perform climate change analysis in RAS?
Which software, sir?
In RAS, Hecras.
Hecras. So basically, we cannot do the climate change, but you can do, sir, with respect, if we have the data as an input from the GCM, RCM, and after the simulations of the statistical downscaling model, and if we have that particular data, then we can input that data from the climate change considerations, and if you input that particular data in the Hecras, then you will be get the output. So you can do the analysis, but the prior thing is that you require the, you can say, the various calculations in the form of the various model GCM, RCM, and the SDSM, and then you can do the input for the Hecras. So you will be get all the parameters.
Any participant? One question in chat box, sir.
Yes, sir. So there is a, okay. So which software is applicable for the water distribution pipe network? Is SCADA is involved for the same as the automation? So for the analysis purpose or the water distribution network, okay. So we have a water James, okay. So that is also a good software.